For more than 4.5 billion years, one star has ruled our sky. Every breath you take, every ocean wave, every forest, city, and civilization, all of it exists because of one ordinary star. The sun, not eternal, not unchanging, but a living, aging nuclear engine, quietly burning through its fuel. And one day, it will die? When we look at the sun from Earth, it feels permanent, unchanging, reliable, immortal. It rises every morning. It sets every evening. Entire human histories have passed beneath its light without noticing even the smallest change. But this sense of permanence is an illusion. The sun is not a solid object. It is not fire, and it is not infinite. The sun is a massive sphere of plasma, so hot that atoms are torn apart into charged particles. At its core, temperatures reach 15 million degrees Celsius, forcing hydrogen atoms to fuse together. This fusion releases energy that pushes outward while gravity pulls inward. This delicate balance is what keeps the sun alive, and it is temporary. Right now, the sun exists in a state of equilibrium. Gravity is trying to collapse it. Nuclear fusion is pushing it outward. As long as hydrogen fuel remains in the core, these forces cancel each other out. The sun shines steadily, providing stable energy to Earth, just the right amount to keep water liquid and life possible. But every second, the sun converts about 4 million tons of mass into pure energy. That mass is gone forever. The sun is slowly consuming itself. Life on Earth is not guaranteed by the universe. It is the result of extraordinary precision. If Earth were just 5% closer to the sun, oceans would evaporate. If it were 5% farther, the planet would freeze solid. The sun's size, temperature, and stability place Earth inside what astronomers call the habitable zone, the narrow region where liquid water can exist. Every ecosystem, every species, every human story depends on that narrow cosmic margin. And that margin is shrinking. Even though the sun appears constant, it is not the same star it was when Earth formed. It is about 30% brighter today than it was billions of years ago. That increase is slow, far too slow for humans to notice, but it is relentless. Over geological time, it reshapes climates, oceans, and atmospheres. The sun is aging. And like all stars, aging leads to transformation and eventually death. In the grand scale of the universe, the sun is not special. It is a medium-sized yellow star, one of hundreds of billions in our galaxy alone. It will never explode as a supernova. It will never become a black hole. It will die quietly, leaving behind a stellar corpse. Yet to us, it is everything. It defines time. It defines seasons. It defines survival. Without the sun, Earth would become a frozen, silent world in just days. For most of human history, the sun was worshipped, feared, or mythologized. But in the last century, humanity has done something extraordinary. We stopped guessing. We began to study our star. We sent machines into space, closer and closer, to understand how the sun works, how it behaves, and how it will one day end. Because to understand the sun's death is to understand the ultimate fate of Earth itself. The sun feels eternal, but in the universe, nothing that burns can last forever. Every star is born with a clock already ticking, and our sun is no exception. Around 4.6 billion years ago, long before Earth existed, the region of space we now call the solar system was nothing more than a cold, drifting cloud of gas and dust. A shock wave, likely from a nearby dying star, passed through this cloud. Gravity took over. The cloud collapsed inward, spinning faster and faster, heating up at the center. As pressure and temperature rose, hydrogen atoms began slamming together with unimaginable force. Then, something irreversible happened. The sun ignited, not in fire, but in nuclear fusion. At that moment, the sun officially began its life. And its countdown. How old is the sun, really? Scientists know the sun's age with remarkable precision by studying meteorites, the oldest solid objects in the solar system, radioactive decay of isotopes, stellar evolution models. All evidence points to the same number. The sun is about 4.6 billion years old. That may sound ancient, but in stellar terms, it's middle-aged. Stars live as long as they have fuel. Massive stars burn fuel fast, die young. Small stars burn fuel slowly, live trillions of years. The sun sits in between. It is large enough to shine brightly, but small enough to burn its fuel slowly and steadily. Its total lifespan is about 10 billion years, which means something profound. The sun is already halfway through its life. Deep inside the sun's core, hydrogen atoms are constantly being fused into helium. Every fusion reaction releases energy, light, and heat, reduces the amount of usable fuel, changes the sun's internal structure. Fusion is not just power, it is time passing. Every second, 600 million tons of hydrogen fuse into helium. 4 million tons of mass are converted into energy. That energy escapes as sunlight. Once hydrogen in the core runs out, the clock reaches zero. As helium builds up in the core, fusion becomes harder. To compensate, the core contracts. Temperature rises. Fusion becomes more intense. The result? The sun grows brighter as it ages. This means the sun of the future will be hotter, more luminous, more hostile to Earth. Long before the sun dies, life on Earth will already be impossible. Earth formed when the sun was cooler and dimmer. Life adapted to that gentle light. But as solar brightness increases, oceans will evaporate. Carbon cycles will collapse. The atmosphere will escape into space. This happens billions of years before the sun's final death. Earth's fate is sealed, not by explosion, but by slow overheating. The sun is not a sudden threat. It is a predictable one. That makes it unique among cosmic dangers. We know when the sun was born, how it generates energy, how long its fuel lasts, exactly how it will die. The sun is not mysterious anymore. It is scheduled. To understand how the sun will die, we must first travel to a place no human and no spacecraft can ever reach. The sun's core. This is where time is consumed, where matter is destroyed, where the fate of Earth is decided every second. From Earth, the sun looks like a solid glowing disk. It isn't. The sun has no solid surface at all. Instead, it is made of layers. The core, where fusion happens. The radiative zone, where energy slowly escapes. The convective zone, where plasma boils upward. The photosphere, the surface we see. The corona, the outer atmosphere, hotter than the surface itself. But everything that matters begins at the center. The sun's core is about 150,000 kilometers wide, roughly the size of Jupiter. Inside it, temperature, 15 million degrees C. Pressure, billions of times higher than Earth's atmosphere. Density, so extreme that atoms are crushed together. In these conditions, hydrogen atoms cannot stay separate. They collide. They fuse. They become something new. Fusion is often misunderstood. The sun is not burning like a flame. Fire requires oxygen. Fusion requires gravity. In the core, for hydrogen nuclei fuse into one helium nucleus. A small amount of mass vanishes. That missing mass becomes energy, exactly as predicted by Einstein's equation. That energy begins a long, slow journey outward. It can take hundreds of thousands of years for a single photon to escape the sun. By the time sunlight reaches your skin, it is ancient. The sun exists because of a constant war. Gravity pulls inward, trying to collapse the star. Fusion energy pushes outward, trying to tear it apart. As long as these forces are equal, the sun remains stable. This balance is called hydrostatic equilibrium. It is delicate, and it will fail. Every fusion reaction leaves behind helium ash. Helium does not fuse easily at the sun's current temperature, so it accumulates in the core like waste at the bottom of a furnace. Over time, the hydrogen supply decreases. The helium core grows. Fusion becomes less efficient. To compensate, gravity squeezes the core harder. The temperature rises. Fusion accelerates. This is why the sun gets brighter as it ages. The sun today is already significantly brighter than it was when Earth formed. This brightness increase is slow, invisible to human lifetimes, but catastrophic on geological timescales. As brightness rises, ice melts permanently. Carbon dioxide cycles break down. Oceans begin to evaporate. The sun does not need to explode to destroy Earth. It only needs to shine a little more. Every fusion reaction is irreversible. Hydrogen becomes helium. Mass becomes energy. Fuel becomes history. Once hydrogen in the core is gone, fusion stops there forever. And when that happens, the sun's structure collapses into a new, violent phase. The nuclear engine inside the sun controls Earth's climate, planetary orbits, the stability of the entire solar system. When that engine changes, everything changes with it. The sun's death will not be sudden. It will be triggered by the failure of this core. For billions of years, this nuclear furnace has sustained life without mercy and without intention. But humans did something unprecedented. We dared to study it up close. We built machines. We left Earth, and we sent them toward the sun itself. In the 1970s, the first spacecraft were sent closer to the sun than Earth's orbit. These early missions were not designed to touch the sun, but to survive nearer than ever before. They taught scientists critical lessons. Solar radiation is far more complex than expected. The solar wind behaves unpredictably. Heat was not the only danger. Charged particles were just as deadly. Every mission revealed new risks and new engineering limits. Each probe came back scarred, overheated, or damaged, but alive. And every survival proved one thing: getting closer was possible. Studying the sun from far away is like trying to understand a hurricane from space. You see patterns, but not causes. Scientists needed to answer fundamental questions. Why is the sun's outer atmosphere hotter than its surface? Where does the solar wind actually originate? What triggers solar storms that can cripple modern technology? These answers could only be found inside the sun's influence, not at a safe distance. By the early 21st century, solar science had reached a limit. Telescopes had done all they could. Models needed real data. And humanity faced a choice: stay at a safe distance, or risk everything to fly closer to our star than ever before. That decision would lead to the most daring solar mission in history. One day, far beyond human history, the sun will stop shining. Not with an explosion, not with violence, but with silence. After billions of years of light, the sun will shed its outer layers into space, forming a glowing planetary nebula, its final act of beauty. What remains will be a white dwarf, an Earth-sized stellar core, dense beyond imagination. Slowly, without the sun's warmth, the remaining planets will freeze. Jupiter and Saturn will drift through eternal night. Moons once warmed during the red giant phase will refreeze. Orbits may destabilize over trillions of years. Some planets could be stolen by passing stars. Others may wander the galaxy alone. Earth, if it still exists, will be a scorched, airless rock long before this final darkness arrives. Life here will already be a memory. Long before the sun's final breath, humanity chose to understand its fate. We built spacecraft. We left Earth. And we sent machines closer to our star than ever thought possible. Missions like Parker Solar Probe did something extraordinary. They flew into the sun's outer atmosphere. They measured the solar wind at its source. They uncovered how solar storms are born. They revealed how stars like ours live and how they age. These spacecraft are humanity's fingerprints on the future, proof that we tried to understand before it was too late. Will humanity be there when the sun dies? Realistically, no. The sun's death lies billions of years ahead, far beyond any civilization we can imagine today. But that does not make this story meaningless. Because the question was never, will we survive the sun's death? The real question is, what will we do with the time we have? The same knowledge that tells us the sun will die also allows us to predict solar storms, protect satellites and power grids, explore other stars, search for new worlds. Understanding death teaches survival. Every atom in your body was forged inside stars that died long before the sun was born. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it came from stellar death. The sun will die one day, but its atoms will live on, scattered into the galaxy, becoming part of new stars, new planets, and perhaps new life. This is not an ending. It is a transformation. The sun is dying, but not today, not tomorrow, not for billions of years. Right now, it still rises. It still warms oceans. It still powers life. And while it lives, we have time. Time to learn. Time to explore. Time to look up at the sky and understand our place in it. Because one day, the sun will go dark. But until then, its light is ours to use.